Hi everyone, welcome to this video, and today we'll be talking about Cramer's rule and the way that it'll be used in circuit analysis to find easier node and loop currents and voltages. So let's dive into this example and analyze the circuit with respect to different parameters that we have, and we'll be explaining how we can use the Cramer's rule in this example with more problem-solving method. Okay, so in this case, following KCL and KVL rules that we've learned from Kirchhoff's using the previous videos, so we are going to analyze the circuit similar to them, but then in the last step, when we have the set of equations available for ourselves, we then need to simplify the analysis using Cramer's rule rather than using method of elimination, because in some cases the number of equations might be larger than expected, as well as the numbers or coefficients might not be that easy to multiply or subtract. So let's get started right away. In this case, we have three loops, as you can see here. And they are represented with nominal currents of I1, I2, and I3. I would tend to start with evaluating the currents that are passing through each element first with respect to I1, I2, and I3. So if I assume that the current that is flowing through this 16-volt voltage source is I1, I would label that as I1, which is flowing upwards. Then I can see that I3 is also exiting that node over here. We can easily ignore IO here because that's an extra variable, which is not different than I3. So we would summarize that as I3. So I3 is exiting this node, I3. Then what is left in this analysis is I3 enters here, I1 enters, I3 exits. So what is left is flowing to the right. But that is also simply I1 minus I3. So I would write I1 minus I3. So this is an inherent nodal analysis that we have employed here. So that is the current passing through this 4 ohms. Now let's try to find out the current passing through this 6 ohms is the same as I3, and I3 is coming all the way down here as I3. We need to be mindful of the current passing through this dependent voltage source. This, even though it says 10 IO, but essentially this is a voltage source. So the current passing through this is not 10 IO, but the voltage across that is 10 IO. Now, the current through that is the same as I2. So we would write I2 as the current that is flowing downwards. Now, in this case, what is left in terms of I3 and I2? So when I3 comes down and I2 leaves that node, what is left? It would be I3 minus I2, which flows to the left. So I3 minus I2 is flowing to the left. Now, at this point, we have a node at the very center of the design where we have two incoming currents to that node. Then you can easily find out what is the current that is flowing downwards. If we sum this and this current, we can see that I3s are going to cancel each out. And what is left is I1 minus I2. So I1 and minus I2 is going to flow downwards. I1 minus I2. So far we could find out all of the currents passing through all of the elements in all the branches. Now is the time to think about different loops and writing KVL. Essentially, we inherently have used KCL when we were trying to find out the currents flowing through the remaining branches with respect to known branches. But now is the time to apply KVL rules. So let's try to apply the rule on loop 1. And loop 1 is something that I'm going to represent that with yellow highlight, for instance. In loop 1, we should start from an arbitrary point, And in this case, I would choose from the bottom left, and moving from bottom left clockwise direction, we enter from negative terminal of the 16 volts. So we start with minus 16, moving on the 4 ohms in the direction of this current. So the voltage drop that is I1 minus I3 times 4. So plus 4 times I1 minus I3. Then moving downwards through this 2 ohms, the current is in the direction of the flow, our movement. So 2 ohms times I1 minus I2 is the voltage drop across that. It would be 2 times I1 minus I2. Now that we have received our reference point, we can conclude this loop to be 0. Now, let's move on to the next loop as the second one, and we can highlight that with another color that I would like to do that with the green one this time. So, starting with an arbitrary position, I would choose that to be the bottom node. So, moving clockwise, we have this 2 ohms first, that if we consider a clockwise direction of the loop, the current is against that direction. That's why that we need to multiply a negative sign when we calculate the voltage drop across that. So for loop 2, that is known with the green color, starting the voltage drop is going to be minus 2 times I1 minus I2. Now we have this 8 ohms. Again, the flow of the loop is clockwise. However, the current is the other direction. So we also need to consider a negative sign when we want to calculate the voltage drop across this 8 ohms. So it would be minus 8 times I3 minus I2. Now we have this last piece that this is a dependent current voltage source, and its value is minus 10 IO. So minus 10 IO in a sense is nothing but minus 10 I3, because IO is the same as I3. So it would be minus 10 I3. Now that we have ended up at our original location, we can easily equate that by 0. Moving on, we'll be looking into the last loop, or essentially this loop. However, it might be a little bit easier for us to start looking at the third loop with something like this as well, that since we have the voltage sources on this current red loop, it would be easier for us to consider the voltage drops, and still it wouldn't be that much different than considering this loop itself. So in loop 3, that we are calling that with the red color, we start in an arbitrary position, and again the bottom node could be the arbitrary position, and in this case we can still move in the clockwise direction, and in this case we enter through this minus 16 independent voltage source, so minus 16. Then we have this 6 ohms that I3 is passing through that. So it will be 6 I3. And also eventually it's going to be this dependent voltage source, which is 10 IO. When we enter from the negative terminal, it would be minus 10 IO. Minus 10 IO. We end up at our original position. Therefore, it would be 0. Now we have 3 equations that we need to first simplify them in order to make them clearly with respect to I1, I2, and I3 unknowns, and then we would be easily applying Cramer's rule. So starting with equation number 1, let's label them as equation number 1, which is here, number 2, which is here, and number 3, which is here. So equation number 1 can be rearranged slightly as follows. We'll do the same actually for equation number 2 and 3 as well. right here. So equation number 1, if I want to keep I1 at very first, what I would have is 4I1 is here and 2I1 are going to sum up to get to 6I1. 6I1. Then in terms of I2, I have minus 2I2. So minus 2I2. And in terms of I3, I have minus 1 times 4. So minus 4I3. Minus 4I3. In terms of the constant, we have minus 16 here that we can easily move it to the other side of the equation. So we would have plus 16. Now, moving on to the second equation. In the second equation, we would start again with I1. We only have I1 with a coefficient of minus 2. So minus 2I1. In terms of I2, we have minus 2 times minus 1, so it is plus 2. And minus 8 minus 1, it would be plus 8. So 2 plus 8, it will be 10. 10 I2. In terms of I3, we have minus 8 and minus 10. So we would have minus 18. Minus 18. And there is no other constant, so we can easily equate that by 0. The third equation. In the third equation, we have this IO, but we forgot to simplify that in terms of I3 because I3 is the same as IO. So I would write that down here as I3 here as well. So minus 16. So we don't have any I1, neither I2. So we would call it as 0. The only coefficient for I3 would be 6 minus 10. So it would be minus 4. Minus 4 I3. I forgot to put I3 in the second equation as well. And the right side is going to be nothing but this minus 16. So if 16 is going to be moved to the other side of the equation, it will be only 16. So now that we have this simplified version of the set of equations, we can easily convert them to matrices. So the coefficients are going to be written as follows. 6, minus 2, and minus 4 are the coefficients of the first equation that I'm going to write it here. The same is going, the second row is going to be the coefficients of second equation. So the second row is going to be exactly minus 2, 10, and minus 18. The third row is going to be 0, 0, and minus 4. So this is going to construct our matrix of coefficients, which is going to be multiplied by the column of unknown variables, or in this case, I1, I2, and I3. Lastly, we have the constants that we have 16 and 0 and 16. So these are the new matrices that we have. Essentially, we can simplify that as matrix A times matrix X equals matrix B, for instance. And in this case, matrix X is simply the unknown variables that we were looking for to find them. B is the results of each equation, and A is simply the matrix of coefficients. So the way that I1, I2, and I3 are going to be calculated is as follows. So for I1, we need to first find the determinant of the modified matrix A. So we would call it as delta 1 divided by the determinant of matrix A itself. I2 is going to be modified determinant of matrix A divided by determinant of matrix A. I3 is going to be, again, delta 3 divided by delta. But then how deltas and delta 1, 2, 3s are going to be calculated? Delta is essentially the determinant of the matrix A, or essentially It's the determinant of matrix A, which is 6 minus 2 minus 4. And then minus 2, 10, minus 18, 0, 0, minus 4. The way that we would calculate this determinant is we would repeat the first and second row again at the very bottom here as well. So we would have 6 minus 2 minus 4 and minus 2, 10, minus 18. So as you can see here, we have this extended matrix that if you want to calculate the determinant, we need to consider the multiplications of the green arrows as well as multiplication of the red arrows that I draw, and then sum them up with positive and negative values, as we'll be doing it right away. So all of the diagonal values along this green arrow are going to be multiplied together. So 6 times 10 times minus 4, and it will be combined with minus 2 times 0 times minus 4, plus it will be 0 times minus 2 times minus 18. So all of them are going to be summed up together. So let's do that really quick and I'm going to write them down with corresponding colors. So it would be 6 times 10 times minus 4 plus minus 2 times 0 times minus 4, and then plus 0 times minus 2 times minus 18. Since that's all for the green arrows. By the way, the red arrows are also going to be multiplied together, but this time there would be a negative sign behind them. So with a big negative sign behind them, minus 4, 10, and 0, minus 4, 10, and 0, then minus 18, 0, 6, minus 18, 0, 6, and the last one, 4, minus 2, minus 2. Well, we need minus 4, minus 4, minus 2, and minus 2. So this whole multiplications are going to be summed up. The green ones are going to be summed up because they are diagonal, and the red ones are going to be subtracted because they are off diagonal. And that would result in the determinant of this matrix. So if we simplify them, we know that these zeros would make all of these guys into 0. Then we'll be left with the first and the last statement. The first one will be minus 240, and the last one would be 16 with positive number. So it would be altogether equal minus 224. So this is the determinant of A. We need to then find out the determinant D1 and delta 2 and delta 3 as well. So in order to do them, we'll use the other slide. So over here, we just copied the matrix A and X and B here as well. Now we need to find out what is the determinant of 1. Determinant 1 is going to be constructed with respect to the determinant of matrix A. So I'm going to actually write it down as minus 6, minus 2, minus 4, then minus 2, 10, and minus 18, 0, 0, minus 4. Now, this time, since we are actually finding the determinant of 1, the first column is going to be replaced by B. So essentially, we'll be writing the column B over here. So it would be 16, 0, and 16. I'm going to highlight that to have a better view, and you can easily see that how column B is going to replace um, the first column of matrix A, and determinant of this matrix is going to be calculated. Similarly, delta 2 and delta 3 are going to be similarly calculated, such that in delta 2, the second column is going to be 16, 0, 16. And in delta 3, the last column is going to be 16, 0, 16. The rest of the columns are going to be taken from matrix A, as I am doing right now. So also try to follow the color code such that delta 2 has the second and delta 3 has the last. Third column is replaced with B, actually, in terms of determinant calculation. Once we could calculate the determinant of each one of these delta 1, delta 2, and delta 3, as we discussed in the previous slide, I1 is going to be delta 1 divided by delta, and I2 is going to be delta 2 divided by delta, and I3 is going to be delta 3 divided by delta. So that will be the general procedure that how the Cramer's rule is going to be applied to find different parameters in a circuit. This is mainly useful when we have more than two set of equations. As you can see here, we have three, and it could be even worse when we have 4 or 5 equations, or 4 or 5 unknown parameters, or when we have large numbers such as 16 or 18 here, that their calculation is not going to be that easy of a method of elimination in general. So this is a brute force method that could be used for such complicated cases. So now that we could find a way to solve a complicated circuit without any constraint on the number of parameters and unknown variables using Cramer's method, here is an exercise that I'll leave it to you guys as a practice at home. And please leave your comments if there is any question regarding this one. Thank you for watching. Hit like and subscribe to the channel if you enjoyed this video.